Cool.
Great.
So we don't have
Yay!
to. I'm disappointed. I did want to serve on that jury, but I was not selected. Um, okay, so let's share my desktop and we're going to get started with
And
today's.
please mute yourselves.
What was the trial for?
It was not a specific trial. It was for a grand jury. So
I see.
so let's get busy and there we go. So last week, of course, I missed, and if you haven't seen it yet, there is a video I have previously pointed you to of a lecture on chapter 2 that I gave early this year. So you can watch that if you haven't already. That'll fill in some gaps for you. The key things that were covered in that chapter include the first primitive experiments that elucidated what goes on in the quantum world and how that set of experiments impacted what was already in the air, as they say. Like, what is the composition of atoms? Why do we see lines, spectral lines, when we look at the colors of atomic species in experiments, so forth? So the early 20th century had a variety of experiments that began to answer those questions. And today we're going to talk about the modern version of quantum mechanics that emerged from that kind of fuzzy business at the early part of the 20th century. One of the key players in this was Richard Feynman. I love this photo. Here he is with a royalty in Sweden when he received his Nobel Prize, looking like a cowboy in a tuxedo. So anyway, he's a great character. If you don't know about Feynman, there's lots of books by him and about him, and you should maybe partake in learning about him. Here's chapter 3's outline. And of course, you can get to the various chapters on a website I've pointed to in the past. If you have problems getting there, if you want to read this material, which I encourage you to do, if you're having problems, get in touch with Alia DU, and they'll help point you in the right direction, or they'll contact me. And let me just say again something I said in the first lecture, and that is I wrote an entire book on this for this class. And I think if you read the book and attend the lectures, you'll get the most out of the experience. Here's a little cartoon version of relating to Schrodinger's cat, Dead and Alive. We'll be talking about what this is all about as we go along. So let's review what was covered in lecture 1 and the video you might have watched of lecture 2. What are the key points that we need to digest to begin to understand quantum mechanics? And among those is the introduction of something called the wave function, which is a mathematical description of a quantum system. And we'll talk about how that, I'm going to show you examples of wave functions. And we get the wave functions from the Schrodinger equation. This is his invention in 1926, 1927, that includes the influence of the environment of the quantum system. And if you understand that environment well enough to solve the equation, the result is the wave function. It's a mathematical function. And as I say, I'll show you some results later this morning. And out of this came the idea from Max Born that the wave function, which is abbreviated by this Greek letter, pronounced like the English word SIGH, psi, that the square of the wave function is a measure of the probability of a certain outcome resulting from a quantum experiment or quantum activity. So that's something I should emphasize. In this course, we talk a lot about the experiments that were done to try to understand quantum physics, but nature is doing quantum all the time. The sun is shining because of quantum mechanical activity that we can describe now because we understand the dynamics that go on inside of a star like the sun. So the universe is filled with quantum things going on, and we have this scheme, wave functions, to describe those activities. And if we square the wave function, we get the probability of some outcome. And this is the beginning of a challenge for the philosophers of science in the past. Prior to quantum mechanics, if you wrote an equation that described a system and solved the equation and it did experiments to confirm the validity of your work, you would get the same result every time. And we count on that. That's how we can fly probes to Mars. You know, they don't go to Venus. They always go where we point them. In the quantum world, that's not true. We can repeat an experiment and we get different results. So that seems troubling because it's the end of determinism. That is, expecting a relationship between cause and effect was a foundational element of science and everyday life prior to quantum mechanics. We now know determinism is set aside in quantum systems. And we'll talk more about this. In fact, it's written right here. If you repeat an experiment, let me get that out of the way. If you repeat an experiment over and over again, you get different results. That's what this says. Different states, that is, different results. But if you run the experiment long enough, you duplicate the behavior of macroscopic experiments. That is, experiments done where we can observe the outcome, as opposed to a quantum system where we have to rely on an experimental apparatus to see the results. We also introduced the idea that particles and waves can each act like the other. An electron, which we prior always thought of as a little entity, can act like a wave. And I'm going to show you examples of that in a minute. And wave stuff, like light, can act like particles. This is one of the big controversies in early days of quantum mechanics, that we have both particle and wave behavior depending on the setting in which you do your quantum manipulation. We also learned that quantum particles can have what is euphemistically called spin. Nothing's actually spinning. What this means is quantum particles in general have magnetic properties. And those magnetic properties it's fortunate that they have those because that offers us a handle on probing the structure of quantum systems. And we will get to that, not today, next time. We also were introduced to the idea of an uncertainty principle that limits the quality of estimate we can make for certain pairs of measurements. I'm not going to go into it now, but we will talk about that. So let's talk about these. Oh, and probably most important is this business of entanglement. We also were introduced in lecture 1 to the idea that distant particles can be connected by a scheme that we do not understand. There's some relationship where a manipulation of one of the pairs is correlated with the behavior of the other of the pair. And indeed, now this entanglement idea has been extended so that it's not just two things that can be entangled. I think the world record is something like 10 items can be in an entangled state so that manipulation of any one of them is correlated with properties of the others without any connection between them that we can identify. So here's the canonical way to talk about the wave-particle duality is this experiment done by Thomas Young in the early 1800s. Light shining on two slits produces this fringe, what we call a fringe pattern. And we now know, and I'm going to demonstrate it for you now, that electrons, these little things that prior to the invention of quantum mechanics were thought to be little microscopic physical entities. Let me make this a bit bigger. Here's it, not an animation. This is a recording of a double slit experiment using electrons rather than light. And you see that individual events are occurring. Little dots are appearing everywhere. But if we run this experiment long enough, we begin to see the fringing. You can see it's already starting to appear. A bright area here, dim area here, bright, dim. This repeats and doesn't run long enough to satisfy me, but there it is. This is based on electrons going through a double slit apparatus, eventually producing this kind of banding that we saw here with the light. So if we treat a quantum particle like an electron in an experiment like this, we see this kind of interference pattern, which implies that there's something wave-like about the electrons. If they all behave like little bullets or BBs, you wouldn't see this. You just see a pile of BBs behind this slit and a pile of electrons behind this slit, but you wouldn't see this intermediate fringing. And that implies that there's something wave-like that's touching both slits. And that thing we now call the wave function. Now, let's scroll down here. I just noticed there's some chat. Let me make sure I'm addressing your questions. Okay, let's carry on. And part of the emergence of a controversy related to quantum mechanics was this idea that we have a measurement problem. I've highlighted it right here. And a measurement problem means that we can use the Schrodinger equation to describe the quantum system, and we get results that are consistent with the Schrodinger equation always, because the Schrodinger equation gives us a wave function, and the wave function gives us the probability for the outcome of an experiment. And that works great up until the point when you actually do the measurement, and then the Schrodinger equation is irrelevant from that point forward. That there's some kind of effect from doing the measurement, hang on, that disqualifies the Schrodinger equation and the wave function from being relevant. In fact, we have this quote from one of the pioneers of modern quantum mechanics, John Bell, that he's wondering what kind of entity has to be involved in carrying out the measurement in order for quantum mechanics to be the right way to describe the subatomic world. For a long time, it was all just laboratory measurements that were relevant. But then the issue came up was, well, can the presence of a human designing the experiment and witnessing the experiment, is that a factor in the way quantum mechanics works? And if that's the case, how qualified does the experimenter have to be? Do they have to understand physics? Do they have to have a PhD? There's even famous quotes from one of the great names in quantum physics, Eugene Wigner, where he thought that a dog witnessing a quantum experiment could make sure that quantum mechanics behave the way we observe it to behave. And that sounds a little ridiculous. Here's another way to look at this measurement problem. Here we have time, perhaps we're in a laboratory, and we're going to measure we're going to describe the experiment we're about to do using the Schrodinger equation, and we will get a wave function, psi, that describes the experiment. And from that, we square that, and we get a range of predicted outcomes. That's what this cloud-like thing is. That's the range of outcomes we expect. And over time, the wave function can change. And so when we're initiating this process, we have a range of predicted values. And then right here, we make a measurement. And all of a sudden, the Schrodinger equation and the wave function are no longer relevant because we have a result. And what happened to the wave function? So the normal way to describe this is that the wave function has collapsed, that it had a range of predictive results coming from this product here, and that all went away as soon as we made the measurement, and we got a result right here. And let's say we are watching that result, and we decide to repeat the experiment, and we go through the same thing again. We have a wave function that's consistent with the description of the experimental apparatus, and we get a range of results, this gray kind of cloudy region, and then we make another measurement. And so this issue of what is it that happens before and after a measurement, that remains to this day a focus of argument and struggle for the physics community to explain what goes on in the measurement process. Even the definition of measurement is a subject of argument. So these are the things we'll talk about as we go along. Now, I've mentioned the Schrodinger equation many times this morning. We don't do math in this class, but we can certainly look at an equation. And this is the Schrodinger equation for a system. And this V here describes the energetic environment of the quantum system, whether it's an experiment or something going on in nature. And we have to solve this equation, and every student of physics learns how to do that. And as a result, we get, here's the wave function, psi, and it depends on position and time. This is the classical way to describe a quantum system. The interesting thing is that right here, there's an I. And that I is something you might have seen in math in high school or college. It's the square root of -1.
Square root of -1.
Yes, which you'll never see this in your checkbook. You'll never see the square root of -1 in what I would call the math of everyday life. And in fact, in most engineering, the square root of -1 only appears as a utility for solving problems. It's an essential part of the mathematical toolkit that scientists and engineers use. And the weird thing is that the wave function we get out of the Schrodinger equation, this, includes this imaginary number. So how real is the wave function? And this is also a confounding issue, that the description of quantum systems necessarily includes a number that doesn't exist in the real world. That's a mystery. The other things here are straightforward. T for time, M for the mass. If this is a particle, we need to know the mass. We have a physical constant here called Planck's constant. It's a tiny, tiny number, and a bunch of mathematical manipulations. So that's what the wave function looks like. I mean, the Schrodinger equation looks like. From it, we get the wave function, and the wave functions can have these odd shapes. So let me skim down here. We're going to talk about the various properties of wave functions. So there again, there's the wave function symbol, the Greek letter that actually is spelled PSI, but the easiest way to say it is psi.
Find your window.
And it describes, let's see, we need people to mute.
Open up to find.
Yeah, because I'm hearing people chatting. So why don't you go on mute so we don't get distracted. So the wave function in a typical system up here, I've just done one dimension. And I'm going to show you some one-dimensional wave functions probably right after the break. But in typical systems, we have to deal with 3 dimensions. So there's a version of the Schrodinger equation that applies in a 3-dimensional space, and we have to solve that to get the wave function. That tells us how the wave function is distributed in space and in time, because the wave functions don't just sit there static. On every quantum system, if you figure out what the wave function is, it's going to change with time. If you just leave a quantum system alone, it will spread out and do various things as it interacts with our environment. Imagine this, that you go to a rock garden and there's rocks in the garden and you pour water onto the rock garden. The flow of the water around the rocks is akin to what happens to the wave function. It interacts with all of space. And in general, it can be infinite in size. It reaches to the far reaches of the universe. In most cases, we can get the right answer by just working on the local properties of the wave function, but it does, in theory, extend through the whole universe. And the square of the wave function gives us the probability of certain events occurring. Now, there's some rules for all of mathematics that the wave function has to be smooth. That's a semi-technical term, but it can't do this. It can't have a kink in it like that, and it can't have 2 values at the same place or at the same time. It can't have a gap. It can't overlap like this. So when the problems of describing a quantum system are dealt with, the results have to accommodate these kinds of boundary conditions. They can't just be any old thing. What's more, we have to take care that if we look at the wave function squared, that's the probability of some outcome occurring, that if we accumulate all those probabilities over all of space, the result has to be the number 1. Because probabilities, if you roll dice, there's a probability of a certain face of the die appearing after the roll, but there's always some result. So another boundary condition on what the wave function can be is that the square of the wave function accumulated over all of space has to be exactly equal to 1. Now, here's what wave functions look like. This is actually an animation. I'll let you, right here is the link. But if you click on this, this is the way the wave function for a quantum mechanical pendulum behaves. And remember, I said the wave function can have an imaginary part because the square root of -1 is included. So this shows both the real and imaginary parts of a wave function as a quantum oscillator goes through its oscillations.
Yeah.
And these results are very intriguing, that how to introduce new mathematical functions to describe this kind of behavior. Actually, we could just jump here and let me show you. Let's make this bigger. In fact, make it now. So you can see what's going on here. As a quantum system oscillates, the real and imaginary parts jiggle around in kind of a graceful way. And that's describing how the quantum system is evolving in time and space under the rules of the Schrodinger equation. And here's a little footnote. If you read this chapter, you see a discussion here of the presence of the square root of -1 and why it's a confounding feature of the way quantum mechanics works. And quantum mechanics does work. Let me emphasize that. Even though we can't explain why we have wave functions that have imaginary parts, and we can't explain the measurement problem, nonetheless, the system works. And we wouldn't have a cell phone or internet or any of the electronic benefits we enjoy from dating back from the 1920s. We wouldn't have any of that without these weird properties of the quantum world putting themselves forward and confronting us and challenging us to understand what's really going on. In fact, in many cases, I would say without quantum mechanics, our life would be more or less like it was in the early 1950s. Would not have atomic bombs because you can't design one without understanding quantum mechanics, but you wouldn't have anything more than the radio and television technologies that existed then. None of the modern medical miracles like MRI and CAT scans and modern computers and the internet and all this rest of this would not exist. We'd all be traveling from place to place on propeller airplanes and riding in diesel locomotive trains. Now, I mentioned that the Schrodinger equation in real life, if you use it to design something like a transistor, you have to deal with the three-dimensional world. And that means understanding how to apply quantum mechanics to the three-dimensional properties of atoms. And these are the shapes of the cloud of electrons floating around a particular atom. I think this is actually hydrogen. For different energy states of hydrogen, you get these very interesting, complicated shapes. So if we go back, well, we can do it here. If we go back to this is a simple harmonic. It's called a harmonic oscillator. It means a pendulum. A quantum pendulum has this very busy sort of thing going on. If we apply the same kind of equation to an atom, we find electrons. The probability of locating the electron has these different shapes depending on the energy levels in the electron.
Copy.
Here's a slice through that. This is the same features I just showed. If we slice through, you can see these beautiful distributions of where the electron is likely to be for the simplest atom, hydrogen, which has a single electron and a single proton. These are the properties that you would expect to see if you could probe the hydrogen atom and look for the electron. And if you look long enough, you would accumulate in this energy level, for example, you get this beautiful flower-like shape, which actually has a three-dimensional shape, but we slice through it to see it in more detail. So we get these interesting results. And the issue of squaring the wave function to get the probability of the location of something, for example, comes from Max Born. Here's his granddaughter, Olivia Newton-John, his late granddaughter, Olivia Newton-John. The idea of squaring the wave function to get a measure of a physical reality, namely the probability of some result from a quantum system, comes from Max Born doing very intricate calculations back in the late 1920s and early 1930s that led him in that direction. Up to that point, the community of quantum scientists were arguing that the wave function itself was physically real. And this there was a huge debate because how can a physically real thing include a number that doesn't exist, namely the square root of -1? So Max Born took everybody by surprise by introducing this idea that all we can really know about the way the physical world behaves is the square of the wave function. And when you square the wave function, all those square roots of -1 go away. So that's very convenient. I mean, the presumption nowadays is he was right. This is the right way to describe a system that has quantum components, but it also avoids dealing with that issue of how is it that the wave function can have imaginary numbers. And there's another footnote here on that subject. At the same time, there was discontent. Heisenberg, the author of the uncertainty principle, wrote on the subject of the loss of determinism that quantum mechanics implies, and says, if we know the present, we can predict the future. That's the way the world worked before quantum. It is not the consequence, but the premise that is false. And he goes on to say, we cannot know all the determining elements of the present. So one argument for why the idea of cause and effect doesn't function as we would expect in quantum mechanics, it's because we don't know everything about a quantum system. We have to, in order to do cause and effect, you have to know everything about the present state if you want to predict the future state. So this is among the first rumblings that we're going to investigate in future lectures about the controversial interpretations of what is quantum mechanics really telling us. Is it a description of the world as it truly is? That is, to take the real, the people that believe that there is a existing quantum world, whether we're looking at it or not. These are the realists. And they argue that the world is real, and the description we have found has some controversial components, but it must be describing the world as it truly is because the theory works. This is not the only philosophy that people embrace. There are others who argue that there is no quantum world until we make a measurement. And we'll get into this more as we get more sophisticated.
Great.
In our understanding. Well, I think I said in the first lecture that the more we dig into these topics, the more difficult it is to digest what the quantum mechanics is telling us. And here's a quote from Einstein. Let's see. Yes, this is Einstein writing to Schrodinger. And let me remind you, Einstein, it's a lot of times it's said that Einstein did not understand quantum mechanics, and it became an embittered old man because of this. It couldn't be farther from the truth. He understood it better than anyone, and he kept asking probing questions about why should we believe that quantum mechanics is a complete theory since it has these controversial elements that we can't explain. And he wrote to Schrodinger that one must assume that the wave function psi does not express the real situation, but rather it is a measure of our knowledge of the situation. And this is one of the alternates to the ideas of the realists, that there is no quantum world unless we make a measurement, and all we're doing is building a theory that enhances our knowledge of the atomic world, but is not a pure description of it. And so he has the rest of this paragraph, he goes on to say that in essence, what he's saying is the wave function cannot be a real thing. There must be something more that we cannot see. And this will come up. And every time we meet, we'll be talking about these ideas. Now, let me just check the time, make sure we're good. Okay. Now, it's important to remember that the pioneers of quantum physics were scientists trained in the 19th century. Mostly they were thermal physicists who found it important to understand why certain phenomena, like the black body curve that I mentioned in lecture 1, why that pertained and so forth. And they had good success. But by the time modern quantum mechanics, the version we know today, had matured in the middle 1920s, the originators of the theory were dying away. Einstein was kind of in the middle of this, but Max Planck and Rutherford and a large number of the pioneers who were so influential from 1900 to the early 1920s, they were fading away. And we got a whole new array of thinkers, people who were not bound by the traditional education that the originators had based on they were young people in the 1880s. And the new people who came along included Heisenberg. In the middle 20s, when quantum mechanics became a mature science, here's what you had. Heisenberg, 23, Pascal Jordan, 22, Pauli. Dirac was the first person to receive a PhD in the field of quantum mechanics. All the others were trained in other branches of physics. And that has its advantages and its disadvantages. When new people come in, they don't know what they don't know. And they're willing to branch out and be innovative and take chances and try to establish themselves professionally. And all these names I just mentioned made significant contributions, particularly Dirac. He was a giant in the bringing quantum mechanics to maturity. Schrodinger and Max Born happened to be a little older. They were in their 50s in 40s in 1925, but the rest of these people were kids. And in fact, in Germany, these shining lights, the new young people were called Kinderscientists or something, meaning they're little kids. And so nonetheless, these young people made their mark by being very innovative and replacing the version of quantum mechanics that started with Niels Bohr's invention of a primitive description of the hydrogen atom. That came out in 1913 and it was very successful, strikingly successful. But more had to be done to bring the theory into maturity. And the young people are the ones that did that. Here's one of the elders, Boltzmann, and he has this famous grave site with an equation. I know you can't read it there, but there's an equation there he invented in the 1880s. He was among those that created the first version of the theory and fainted away. So now let's move to a key element of quantum mechanics that became unavoidable in the 1920s. There had already been this debate about the nature of light. You remember Thomas Young in the early 1800s did the first double slit experiments and said, the only way we can get those kinds of results is if light is propagated as waves. Prior to that time, Newton had asserted that light is particles he called corpuscles. So both theories had standing through the early part of the 1800s. In the 1860s, James Clerk Maxwell created a description of electromagnetic waves that we still use today. And that led emphasis in the direction of wave-like properties of light as opposed to particles. But then there were experiments in the early 1900s that suggested that light behaved like particles. Einstein was instrumental in explaining those experiments. So by the 1920s, there was still a debate, and Einstein, who believed in light being made up of particles, was in the minority. He was isolated intellectually because he kept insisting that light could exist as particles of energy we now call photons. And it wasn't until some experiments were done in the late 1920s that it became obvious that light could behave as either waves or particles. Then Louis de Broglie, 1925, he said, well, if light can be particles or waves, depending on the kind of experiment you do, shouldn't it be true that particles, an example would be electrons, that electrons should have wave-like particles if we do the right experiment? And this was very controversial. It's a part of the work he did for his PhD thesis. He and his brother were rich aristocrats, and they had in their mansion in France, they had built laboratories to study nuclear physics and a variety of other things. And ultimately, de Broglie turned out to be the more talented of the two and wrote his thesis on this idea that a particle can behave like a wave, and presented that result in his controversial PhD dissertation. And within 6 years, he won a Nobel Prize because experiments were done to prove that electrons can behave like waves. A lot of that work was done here in the United States. Davison and Germer, working on metallic alloys, noticed wave-like behavior when X-rays interacted with the crystal lattice of the metals they were working on. This is a cartoon of a modern thought experiment invented by John Wheeler, a very influential American physicist. We'll talk about this later. I want to describe this in detail, but I don't want to do it now. So one of the direct consequences of de Broglie's argument that particles can behave like waves and vice versa is the eventual development of electron microscopes. So here's a microscopic vegetable. It's a plankton floating in the ocean. And this is about the best you can do with an optical microscope looking at this particular type of vegetation. But if you switch to an electron microscope and treat the electrons as waves, they can produce this kind of image, where you can see a dramatic improvement in the resolution of the details associated with this. So understanding the theory of particles and waves also has led to practical applications. Now let's get into the results of manipulating the Schrodinger equation. We're not going to do the math, but I'm going to show you what every physics student encounters in their early in their education. One question is, what are the energy levels of a quantum particle in a box that has infinitely thick walls, an impenetrable box? And here that box is drawn in one dimension. So it's like a very deep Grand Canyon with infinitely high walls. And you put a particle in here and use the Schrodinger equation to figure out the energy levels that the particle can have. And by using the techniques of mathematics that engineers and scientists are introduced to, we find the energy levels look like this. So let's review quickly what these symbols are. There's the Planck's constant, the mass of the particle, the width of the box here is A, and then this is what is key. N represents integers, 1, 2, 3, and so forth. But in no case can N equal a integer with a fraction, like 1.2 or 2.6 or anything like that. So we see an early result directly from the Schrodinger equation that the energy levels of a particle in this kind of infinitely deep well are quantized, because the values that you put in here for N can only take on integer values. Here's what the wave function looks like if we expand that box into 2 dimensions. It has this very interesting bumpy shape. This is the wave function. So this, if you square this, you get something that looks something like this. And it tells you where you would probably find the electron if you could probe this microscopic box and look around and see where do I most frequently see the electron. It's there or there or there or there, and with equal probability. So we have a way to talk about experiments using the Schrodinger equation. Now let's try a different version of this well. In this case, the walls are not infinitely hard. They have, for example, this could be a can. Like if you put an electron in a tin can, there's walls there confining it. But when you do the calculations, you discover that here, the probability of the electron being outside the can is not 0. Here's another way to look at it. This is the infinite well, and the electron has no ability to penetrate the walls. But if we make the well not infinitely deep, there's some penetration that can occur. This is called tunneling, and this is used in the design of transistors. In fact, your cell phone has special transistors that rely on this tunneling effect. And it comes right from the Schrodinger equation. If you can describe the environment of a quantum thing, in this case, we're talking about electrons, if the walls are thin enough, there's a chance the electron can pop right through. And there's interesting extensions of this, like you can have something that looks like a comb, and then you get more interesting results. Here's what happens if you have a quantum particle bouncing in a gravitational field. Like if you could make an elastic quantum particle that you drop like just like dropping a basketball, it bounces, you get a wave function that looks like this. All of this comes from the Schrodinger equation and its solutions. We can also compare different atoms. What we have here is in a hydrogen atom, where are we most likely to find the electron? And then that place is right here. The blue line is what you would get if you deal with helium, which doesn't have a single electron, it has multiple electrons. So, and you see here, this is the square of the wave function. So we get all these intricacies, and here's more on this tunneling business. Once tunneling was understood, that's what's happening here. George Gamow, who was a young scientist in Russia at the time, or Ukraine actually, I think, he realized that some types of nuclear radiation could be tunneling of particles in the nucleus that managed to pop out of the nucleus because quantum mechanics allows that to happen. And he proposed in the late 1920s that nuclear decay could result from tunneling of a, a group of neutrons and protons just popping spontaneously out of the nucleus of a heavier atom. And that's exactly what is seen. So we have these various radioactive isotopes, and nuclear tunneling is the reason that they slowly decay. Now, here's an example, a game you can play. I'm not going to do it now, but this comes from a set of simulations done by a university in England, where they have the students build these various kinds of animations, and you can see the decay of polonium to an isotope of lead. And you see it's in a cartoon version, so you can control some of the properties, and tunneling is part of the calculation here. We've already talked about the electron microscope. There's an even more advanced version called a scanning electron microscope that has this, it exploits this property of the Schrodinger equation that lets electrons penetrate a barrier. This led to a Nobel Prize. This is a picture of what is called a carbon nanotube, where the distance, well, these are individual atoms that you can see because you exploit the tunneling effect by having a tungsten tip, a needle so fine that it has just a single atom at the end. By scanning that over one of these microscopic tubes, these tubes look like those tubes we used to have as a game where you put your fingers in and you can't get both fingers out. It's a woven thing. That's this carbon nanotube, and those are individual atoms that you can detect using this technology, which exploits tunneling. So we're about to get into another area, how the wave function changes in time. Well, I guess I'm just thinking about taking a break here in the next few minutes, but let's go through this. I mentioned that wave functions are not static. If you create a quantum system and you leave it alone, the wave function will change. And here's some examples that I conjured up. If you have a small particle confined in a quantum mechanical environment and you just leave it alone, the wave function starts out looking like this and eventually ends up looking like this. For a small mass, it spreads more. For a larger mass, it spreads, but not as much. So again, the wave function is sort of like water. Or another example, I used a rock garden a minute ago, but you could say if you just pour water on your fingers, some of it's going to leak through. The quantum system does not want to stay static, and they spread out sort of like this. Okay. So we're going to get into the uncertainty principle now. But let's take a break. It's 10:28 according to the time standard. And let's come back at 10:35. That gives us 7 minutes to take a break and get a sip of water. Okay.
Fairy tale. Hush.
Okay, folks, I'm back. A couple of things to add. These are the Chinese finger traps that I was talking about, where you put your fingers in. And this is what those carbon nanotubes look like. It's kind of a fabric of a microscopic, tiny little tube where the alternating colors represent atoms. So with scanning tunneling microscope, we can actually see the atoms associated with those, and they're extremely close together. Now, I also see a conversation going on here, comments about how to interpret this idea of unpredictable results that have probabilities. Namely, this is gets into the business of statistical analysis related to human behavior. Each person takes their own path from place to place or from one idea to the next. And it's unpredictable. Their background and their environment would dictate how they choose to deal with something. But on the whole, we get a result that's statistical average. And that's kind of the way quantum mechanics works. Maria has a question.
Yeah. Has there ever been an anatomical study of the brains of people who understand this? Maybe you could donate your brain to
Well,
see what the difference is between those brains and my brain.
there have, I'm thinking about musicians now, not quantum scientists.
I see that you're a musician, like my
Well,
son.
I'm a music student. I'm not a musician yet, but but there have been studies done of people with extraordinary musical talent, and I don't know of many scientists who've donated their brains. Einstein's brain, there's a book about it. It's called Travels with Einstein's Brain. That's kind of a humorous but true account of what happened to his brain. And
Oh.
so, no, there's, I don't know of any serious studies. All right, so let's do our thing here. Uncertainty principle, which comes from Heisenberg. And here's the essential thing. As soon as you have any system that is described by a wave, immediately you can conclude that your ability to fully understand that system has limitations. And let me tell you of an example that all the scientists that I've discussed knew about, and it has to do with how light travels through lenses or reflects from mirrors acting as focusing elements. The physics of this was understood since the very early 1800s. And what it tells us is even if you design a perfect lens, because there are boundaries to the lens, you cannot make an infinitely perfect focus. If you have light propagating toward this lens and look at the properties at the focal point, you don't get a little spike, an infinitesimally small spike. You get a blur. It actually has some rings around it. This is the result of what is called diffraction. It's a direct result of the fact that light encountering a lens in an optical system like your eye or glasses or telescopes, the light behaves like waves. And the focus can never be perfect. And Heisenberg was certainly aware of this when he was thinking about what is the consequence of the fact that we have a description of the quantum world that relies on a wave. There must be some limitation akin to this, a limitation associated with light encountering focusing elements. And from that thinking, we get this.
Oh. Okay.
This is the uncertainty principle that says that the uncertainty in your measurement of momentum of a particle and the position of the particle has a limitation. It can never get below this number. Number h represents Planck's constant, which is a tiny little number, so it's irrelevant for everyday life. We don't see any effect of this in our everyday lives, but if you get into the quantum world where things are small, then it becomes a foundational issue that if you measure the momentum of a particle and measure its position, you have to give something up. One of them, if you want to make the momentum measurement very, very precise, you have to give up the position measurement. It's going to be uncertain. And there are all sorts of jokes about this where the policeman stops Heisenberg driving on the highway and says, "Do you know how fast you were going?" And Heisenberg says, "I know exactly how fast I was going, but now I don't know where I am." So, and there's a corresponding principle that relates to energy and time. What this says is that if you want to measure the energy of a quantum particle very, very precisely, and people want to do that, they do experiments all the time in accelerator facilities and other experiments, and you want to measure the energy of things very, very precisely. To do that takes a long time. It also implies that if you look at something for a very short time, highly energetic particles could be there. And that we will talk about in a little bit because it has a profound influence on what we know about the quantum world. So we have the uncertainty principle described here in the case of light passing through a focusing system. Another way to look at this is here's the position of a particle and here's its momentum, which is related to its velocity. And if you want the momentum measurement to be tiny, the position measurement has to be broadened out, so you're less certain about the position, and vice versa. Somewhere else in the book, I have a picture of somebody who has made an animal out of balloons. If you squeeze that balloon animal to confine it in one direction, it will bulge in the other direction. It's an unavoidable property of any system that is described by waves. Let me make this a little
More confusing.
What's that? You asking a question? No? Okay. Just remember to mute if you're not, unless you want to ask a question. Okay. So here's the way it works in the mathematical jargon. If we have a wave function that looks like this, that is a very confined wave function in position, the momentum wave function bulges out. And if we have a lot of uncertainty about the position, if this is the wave function, then we have a much more confined momentum estimate. And this comes right from the mathematics. Originally, Heisenberg's idea was conceptual. But once people thought about it, they said, oh yeah, obviously, if we look at wave-particle duality, we can see why the math tells us that a confined wave function must have a large momentum and vice versa. So I've listed in this table some examples of uncertainty. Here's the one that relates energy and time. Here's one that pertains to the double slit experiment. Here's one for a particle in a box. Remember, I showed you that particle in a confined box. If you make the box narrower, if you make it smaller, the energy levels change because of the uncertainty principle. So now let's look at some experiments that confirm the theory. There's obviously quantum mechanics works. Otherwise, we wouldn't be talking over the internet. We'd have to be in the same room to discuss these topics. But the experiments are really compelling. For example, in the late 1920s, Einstein got a letter from an unknown scientist in India, Bose, who had been working with the first versions of modern quantum mechanics. And he noticed something. He noticed that if the properties of the quantum system were such that atoms could interact with each other strongly, that a new kind of material could be formed called a condensate. And he wrote to Einstein and said, I've got this theory, I've done all the math. Can you make sure that my paper gets published in a significant journal in Europe? And Einstein was very taken with this and did additional work on Bose, who was doing statistical analysis of groups of atoms. And it took another 70 years, but people, including two guys from the University of Colorado, managed to produce Bose-Einstein condensation by cooling a particular group of sodium atoms down to a temperature so close to absolute zero that the group of atoms were described by a single wave function. And you see the temperature above absolute zero is a tenth of a millionth of a degree above absolute zero. They were the first to demonstrate Bose-Einstein condensation and won the Nobel Prize in 2001 for that. This was a prediction that turned into a measurement. And here we see this is data from the experiment as the temperature in the system was reduced. And now this is an everyday thing. There's a company in Boulder called Cold Quanta who will sell you a machine for creating Bose-Einstein condensation. So you can do experiments with this kind of exotic material. To do that, again, you have to be able to get down to extremely low temperatures. Here they're talking about 130 billionths of a degree above absolute zero. So if you want to buy one of those machines, I don't know, they're like $500,000 or something, and a university might want to buy one of those so their students or their researchers can explore that part of the quantum world. Now here's another prediction of quantum mechanics, and this comes from the uncertainty principle. I mentioned the uncertainty principle says that, let's go back and don't get dizzy. This is a version of the uncertainty principle relating energy and time. And what Casimir, a Dutch scientist, predicted in the late 1940s is that a pure vacuum would be churning with particles popping into and disappearing from existence in very short times, but that there should be energy in an empty volume of space. And he proposed an experiment. I won't go into it in much detail, except to say it requires you to have two plates extremely close together. And then you can measure, if you design a good experiment, you can measure the force of the energy between the two plates. It took 50 years to develop the experiment to a point where it works. And here's what you get. The red line is Casimir's theory, and the dots are the measurements made in a modern Casimir experiment. And you can see the agreement is extraordinary. This suggests that empty space is filled with what is sometimes called quantum foam, churning array of particles of all kinds of light of all frequencies just popping into and leaving existence because the uncertainty principle allows that to happen. Let me check the chat here. What are the other four states of matter? Is it solid, liquid, gas, and plasma? And the energy in the vacuum behave as particles or waves. Well, it depends on how you want to experiment. What kind of experiment did you design? And in the case of the Casimir effect, I don't think it matters. What's the key thing is there's energy in the vacuum between these plates. We also mentioned that quantum mechanics includes the influence of what the physics people call spin, but it's actually magnetic properties. And this is one of the most extraordinary results from quantum mechanics. The theory, here, let me do it this way so you can only see the theory. The theory predicts this number, the magnetic property of electrons. This comes from work in the late 1940s by Feynman and two others. Working independently, all three got this number for the theory for a measure of the magnetic properties of the electron. And there's the measurement. And you can see they agree all the way out to this digit. This is the most precise prediction in the history of science. And so, and obviously these people were using the properties of quantum physics that they understood at the time to make this prediction. And it comes out right. A deep, deep mystery in quantum mechanics that has now been proven in laboratories. It took a long time to figure out how to do it, but it's proven in laboratories is this issue of entanglement. I talked about this some in the first lecture, and what we're talking about here is under the right circumstances, pairs of particles or groups of particles created in the right way have this property of entanglement, that a single wave function describes the whole group. It's sort of like the condensation thing that Einstein and Bose predicted in the 1920s and eventually was found in Boulder, Colorado. Entanglement has this mysterious feature that there's some correlation between properties that are entangled without any connection existing between them. Now, how do we know there's no connection? And the answer is we build these experiments so that we can separate observers so far that even light cannot travel between them quick enough to somehow make entanglement appear. So here's a cartoon that makes it easy to talk about. It's hard in reality to do these experiments, but they are done all the time now. Indeed, now this is a standard experiment in undergraduate physics, that you build a system that has some kind of a source of, in this case, light, photons. And the source has the property that a photon can be emitted in the direction to our protagonist Alice, and another one will go in the opposite direction to her friend Bob. And the properties of these two are always, one has a spin of one orientation, the other one has the opposite spin. And then the question is, what happens when Bob makes a measurement? Well, he gets a whole string of these photons and he writes down all his numbers. There they are. He's written them all down. And he keeps track. The first one was, in this case, they're using zeros and ones to indicate the spin orientation that Bob detects. So he writes that all down. And then when the experiment's over, he goes and visits with Alice, and she's been doing the same thing, and there's her results. If you look closely here, I can't make it any bigger, or can I? I don't think I can. But every time he got a 0, she got a 1. And every time she got a 0, he got a 1, and so forth. So there's this, in the ideal case, there's this high level of correlation between the detections that Bob got, even though all of his are random. Each photon he gets has a random result of a 0 or a 1, but he's completely correlated with Alice's results, as if something happened when Bob made his measurement to cause Alice's result to collaborate somehow. But there's no, these two experimenters are so far apart, even light could not go from one to the other and somehow signal, oh, Bob got a 1, Alice, you better get a 0. And this remains one of the deep, deep mysteries of quantum mechanics. And it's being exploited now in development of modern versions of quantum computers and cryptology. Yeah, there it is. Warren just asked the question I just answered. Is this used in message encryption on our phones? Not yet. Not yet, Warren. The concept exists and it will be put to use in encrypting data in a way that cannot be broken. And preliminary experiments, I think one of the big phone companies did some experiments using quantum entanglement to encode messages in a way that cannot be broken. Here's Madame Wu, famous Chinese nuclear scientist, who in the early 1950s, probably without realizing it, was the first to detect entangled particles. She and her student were working with radioactive materials, making measurements of the polarization of some property, doesn't matter what it is, of the particles that come out of nuclear decay. And they were actually measuring duplicate particles. So in certain decays in certain materials, 2 particles come flying out. And they were measuring the properties in a way that if they had known what they should have been looking for, they would have discovered entanglement. Nowadays, entanglement is an everyday thing. And we will not in this lecture, I think in lecture 5, I will show you an array of experiments that now use entangled particles to demonstrate all sorts of weird properties of the quantum world. And a way to describe how Einstein would have dealt with this outcome is the following. And it's been said this way, that of all the ideas that Einstein protested when he was writing about the reality of quantum mechanics, the truth would have been the version he liked least. He protested against this idea of what he called spooky action at a distance, or the implication from Schrodinger's equation that particles could be created in entangled pairs and interact with each other by some unknown mechanism, no matter how far apart they are in the universe. Einstein protested against that, and he was wrong. We now know by doing experiments that sort of behavior can happen. And indeed, the Nobel Prize of 2022 was awarded to 3 people we will meet in detail in a future lecture who actually did the experiments to prove that entanglement is a real thing. Now we come to another application of quantum mechanics, and that is the ability, hang on, I gotta click on something. the ability to build a periodic table. One of these days I got to fix this. I got a typo there. So Feynman said, and everybody agrees on this now, that all of theoretical chemistry is just physics. Here's the periodic table as it existed in the 1860s. This is Mendeleev's periodic table, teased together by looking at chemical interactions of different kinds of elements that were known at the time. Not every element was known. For example, you see he's got hydrogen here, but he does not know about helium. That wasn't found until maybe 20 years after his experiments with different chemicals and their interactions. And all of the right way to say this is all of chemistry has to do with the electron clouds that are around the nuclei of different atomic species. That's what chemistry is the interaction and repulsion or connection between atoms because of the properties of their electron clouds. And you see this is quite modern. I mean, he understood carbon has 12, neon has 14 electrons, beryllium, lithium. He's got the standard nomenclature here. There's lead, for example, thorium, uranium. Now, how do you build this once you know about quantum mechanics? Niels Bohr was the first to do this. Remember, I mentioned Bohr in 1913 produced a primitive description of the hydrogen atom, which predicts all of the properties we observe, the spectra, the physical constants that are related to the spectra. All of that came out of Bohr's primitive model of the hydrogen atom, which we now know is wrong, but his model works because hydrogen is such a simple atom. But once you understand how the electrons are added to build heavier and heavier elements, starting with hydrogen here and eventually getting to the heavier elements, you can build the periodic table. And he was very successful in the 1930s building an early version of this. This is the modern version. And this is the version that comes from the cosmologists, showing that hydrogen and helium were produced in the Big Bang and a tiny amount of lithium, and all the rest of this, except the human-made synthetic atoms, were made in stars or stellar explosions. So let's look at, and along the way, other effects were seen. If you put lithium into an environment with an electric field, you can see the energy levels change. So you need a scheme, and quantum mechanics gives us this, a scheme for predicting how the energy levels that we observe in an atom like lithium change if you put this in an electric field, and a similar effect in a magnetic field. And the building of the periodic table and the explanation for these behaviors comes from this, the Pauli exclusion principle. Wolfgang Pauli was one of the kids who emerged in the 1920s and made tremendous contribution to the science of quantum mechanics. And what Pauli said is, when electrons in an atom are in the same state, one of them has to change its state. They can't be in the same state. Schrodinger's equation, if you look at things like the energy level, is quantized with the letter N, and the spin angular momentum is quantized with this letter L, and M sub L is this, quantizes the orbital angular momentum. These are the properties of atoms. The electrons in atoms have these quantum numbers. And no pair of electrons, but Pauli says, can have the same set of numbers. And what does that do? That produces effectively a force. If you try to jam too many electrons into the same energy level, that is, they have the same value of N, physics won't allow it. It forces something to change. And we're going to scroll down here. There's a lot of deal here. Let me tell you how this works. 50 years ago, I had two friends. They were dentists and they were really bored. And they got into the business of promoting rock and roll shows. And I was friends with them, and I used to go to see the shows. I would go and help unload the truck and so forth. And eventually I became the announcer, the stage announcer. And we had, on occasion, we would have an event where the front row expensive seats had not all been purchased, but the rest of the cheaper seats were filled. And it was my job to go out and explain to the crowd that because the empty front row seats are not full, if you come down in an orderly fashion, you can fill those seats. Now, this, of course, made the people sitting who had purchased the expensive seats, it made them frustrated, but this is what we did occasionally anyway. And it was an orderly progression. I'm trying to think if we did something like pick a number or something. So we picked people out of this crowd to come down and occupy these seats. This is kind of like the lowest energy level in an atom. If there are empty spaces, the electrons will move down here and emit light when they do it, leaving empty spaces up here for other electrons to join. So eventually, after we invited people to fill the front row seats, we had something like this going on. But we never allowed this, where there were just crowds of people forgetting about seating. They were all standing up, crashing into each other. This was an orderly process of filling the lower energy states. And if two people tried to get into that seat, an usher would stop them. One of them had to leave and go back farther. And that's the Pauli exclusion principle. There's room for one electron with its unique quantum numbers to occupy each space in an atom. And again, the Pauli exclusion principle does not allow this. So with that in mind, let's build some atoms. What I'm listing here are the energy shells. You might remember this terminology from your days if you took chemistry. So we can have one electron. This is hydrogen. We can have one electron in the lowest energy state. And you see that's an arrow. There's the tip of the arrow. And we can have one electron there.
He'll come.
What's that? Do you have a question? Yes? No?
Somebody needs to mute.
Yeah, let's mute if you're not asking a question. Okay, so what happens if another electron shows up and we want to see if it can fit into this hydrogen atom? Now, the nucleus has to cooperate, but we can add another electron. But see, this one has a down spin. This represents the spin, and these have quantum numbers, and so everything's fine. Helium can have a lowest energy state with one spin up and one spin down. If you want to go to the next level, you have to create lithium, because there's no room here for another electron to occupy this lower energy state. There's the energy level, 1. There's the spin states, 1 up and 1 down. So everybody's happy here. And the next electron has to occupy this second energy level 2s. And then there's room there for another electron with the opposite spin. And now you've created beryllium. And boron, same thing is going on. There's no room to add another electron, no matter what its spin is, because these two shells are already filled. And there's a terminology, it appears here, that you have one electron in then two electrons and two electrons. And so if you keep doing this, you get this accumulation of electrons in incrementally larger energy levels because there's room for different spin orientations. And if you exceed the numbers of allowable states under the Pauli exclusion principle, you end up with a periodic table. And here's the periodic table all the way up. There's plutonium and so forth. And as you're doing that, you're altering the positions where you're most likely to find the electrons. These are the wave functions, the predictions of the probability of finding the electrons of argon. So you get its lowest energy electron, this is where the nucleus is, where it says 0. You get, in its lowest energy state, you have 1 electron there and 4 electrons clustered there. That's argon. Here's the same thing for neon. You get this 1s energy level. It's going to have 2 electrons, 1 of each orientation. And then you have this group of 4 and so forth. And so again, here's the periodic table. And if you look closely, you can, this shows the size of the electron clouds of the various atoms in the periodic table. Let's see if I can, yeah. So there's hydrogen. Right below it is lithium, and the cloud, this comes from the Schrodinger equation, calculating the probability of where you find the electrons. There's a cloud where you find the electrons here for lithium and sodium, calcium, titanium, and so forth. So using the Schrodinger equation and doing numerical calculations to get the wave functions and squaring the wave functions, we get these probabilities where the electrons live. And these are the energy levels that you're familiar with from chemistry. So we're able to build the periodic table. Now, to do that requires that we work in 3 dimensions. So again, here's the Schrodinger equation in 3 dimensions, and it's a lot more complicated, except if you look closely, it's got the same key parameters. There's Planck's constant that was found in 1900, the mass, and the rest of this is just mathematical tools. There's a number 4 and pi and something, but it's the same kind of thing we saw before the break. So this is the equation you have to solve in 3 dimensions to get these predictions of where the size of the electron clouds. To get that accurately, you have to do these calculations. And they have been done. So what we see is the solution of the Schrodinger equation gives us the energy levels as a function of integers. That's why the word quantum is used in describing this theory. Everything depends on integers. Here I emphasize it right here. The integers 1, 2, 3, 4, and so forth. Nowhere here do the equations result in results like 1.2 or 2.6 or something like that. And here's Niels Bohr's energy level model for hydrogen It involves the charge of the electron, the mass of the electron, Planck's constant, some physical constants, and there is the letter N indicating integers 1, 2, 3, 4, and so forth, that tells us the energy levels of hydrogen depend on the inverse square of integers. And it works. This is Bohr. This comes directly from Bohr's model. If you do the modern version that we're going to see here in a minute, you get the same result. That's one of the great mysteries that I encountered in my education, is how was it that Bohr got the right answer with a model of hydrogen that we now know is incorrect. So we've seen this before, and we can actually see these things. We can see the electron clouds in various experiments, and there's a discussion here you can follow up on if you're interested, of how this kind of imaging of the electron clouds is found in an experimental setting. Now, I mentioned that we are going to see the modern version of quantum mechanics. It appears in the late 1920s, propelled forward by Paul Dirac, the first person to get a PhD in quantum science. And the idea is to understand how electrically charged particles interact with matter. Dirac was a pioneer in this, and you see in 1928, he produced an equation that actually appears in lecture 1. It's very elegant. It's the one that appears next to the nude sketch by Picasso. It just, in just a few lines, Dirac was able to capture the behavior of how electrons interact with matter. In the process, he discovered that there must exist an antiparticle of the electron, we now call it the positron, and opened up a whole new field in physics to the idea that fundamental particles have antiparticles. That, for example, in the case of the electron, it and its antiparticle, the positron, have the same mass but have opposite charge. When they get together, the electron and the positron, there is an explosion of energy, and the mass of both of them disappears into an array of charged tiny particles that are temporary and a puff of light. So this, in the late 20s, is the beginning of the more modern version of quantum mechanics that allows us to explore the world of antiparticles and subatomic particles, such as the muon. This is a massive version or member of the electron family that we find coming down on us from cosmic rays, high energy particles that strike the atmosphere, produce showers of subatomic particles. Muons and others are found by studying those particles. At the same time, the ground was being set for people like Casimir. I already discussed his prediction that empty space should be filled with virtual particles, because the uncertainty principle allows those particles to exist so long as the interval over which they exist is short enough. So Dirac was a pioneer right at the beginning of this whole business of understanding how subatomic particles can pop into and out of existence. What's more, progress was made in understanding what an electron looks like to its neighbors. Because of virtual particles, here's a negatively charged particle, could be an electron. This object ends up being shielded by virtual particles. because of its presence, any virtual particle that pops into existence is attracted to the negative charge here. And that leads to virtual particles around this area, all ending up in a weak cloud of what looks like a negative charged item. And this impacts the energy levels that are found when detailed experiments are made of electrons, because each electron is shrouded by virtual temporary particles that pop into existence and then disappear. And measurements that were made, very exquisitely precise measurements, showed subtle little differences in the energy levels in all the atoms. Bohr, for example, predicted the energy levels in hydrogen. When Dirac's theory of virtual particles was included, we find that this energy level predicted by Bohr actually is two energy levels very close together. And then the modern version does even more of this kind of looking at the implications of the existence of virtual particles that are present in every atom, shielding all the electrons that form the cloud around the nucleus. And using technology invented related to radar in World War II, these measurements are now an everyday thing. And again, I showed you this before. Doing the calculation, we get this number, and doing the measurements, we get almost exactly the same number. There's more to entertain you here. In addition, we have this very interesting connection between quantum mechanics and Erwin Schrödinger. In 1949 or 48, Schrödinger wrote a book called What is Life? And he speculated, now keep in mind, this is before the discovery of DNA. Schrödinger speculated about what must be the information repository in the cells of animals and plants that are conveyed from one generation to another so that there's heredity can occur. Otherwise, every animal would give birth to a completely different species of animal. And here's a letter from Francis Crick in 1953, just before Crick and Watson won the Nobel Prize for their understanding of DNA, thanking Schrödinger for his insight into the structure that must exist in cells where, right here, Schrödinger had predicted there should be some nearly periodic crystal that forms the repository of information that is conveyed from parents to child. And indeed, it turned out that's DNA. So Schrödinger's book is based on his understanding of atomic and subatomic physics. Here are the guys that did that exquisite calculation of the magnetic properties of electrons. Feynman, Julian Schwinger, both Americans, Tominaga, Japanese, using different techniques, were able to calculate the magnetic property of electrons that was ultimately found in experiments, and they won the Nobel Prize in 1967. The interesting thing is that none of the three could understand how the other three got their results. They all got the same result. There was somebody who knew how each of their techniques worked, and that is this guy, Freeman Dyson. Freeman Dyson studied what Feynman did, Schwenger did, Tominaga did, and showed that their techniques were equivalent, but used different approaches mathematically and technically. And if you read this, you'll see that I met Freeman Dyson once, and he was a tiny little man with a gigantic brain. Now, what we've just talked about for the last 6 or 7 minutes was quantum electrodynamics, the interaction of charged particles with matter. Nowadays, students are quickly brought to a new way to work with quantum theory, and it's called quantum field theory. And in quantum field theory, there are no particles. There are fields, a disturbance in a vacuum that, under the right conditions, facilitate the presence of particles. So light is an example. This is where we can finally come to a resolution of whether light is particles or waves. The modern interpretation is that an electromagnetic field, the one that was described by Maxwell in the 1860s, can produce a disturbance in the field that we call a photon. Without some mechanism for disturbing the field, there are no photons. There's also an electron field. Without disturbing the electron field, there are no electrons. And so the difference between particles and waves is now set aside in favor of quantum field theory, that there's only a field. And if you do the right thing, like turn on a flashlight or something like that, you're creating photons, which are disturbances in a pre-existing electromagnetic field. And we can't do much with this in this class, but the idea is there is a new modern way that has been embraced because it allows the application of field theory to nuclear particles, namely neutrons, protons, and their components. And here I've highlighted a typical quote about fields. Fields are properties of space, not a substance. You can't see the field. If you disturb the field, you see the particles. But for practitioners in quantum fields, there are only fields. And the idea of fields dates back 200 years. So it was sort of around, it was a tool that could be exploited to describe the quantum world. And now it is in full use to describe the components of atoms, namely protons, neutrons, and electrons, as well as all these other particles that are part of the subatomic world. And we'll talk about this more in future lectures. There's some words here about this quantum foam. This is the virtual particle stuff that can exist and is justified by the existence of fields. Again, here is Nobel Prize winner Steven Weinberg saying, nature is fields. Particles are just a derivative phenomenon. So there's more on quantum field theory here. I tried to write it in a way that's readable, so perhaps you take a look at that. And there's some problems with it as well. And I think, unless there are questions, we got 2 more comments. Let's see. Rich says, is there thought maybe an undiscovered dimension could be providing the communication? We don't know. And it does require entanglement. Rich's question pertains to entanglement. We don't know how that entanglement correlation occurs, but it happens faster than light can travel. We know that. And experiments have been done using satellites and so forth. That's part of the reason that the Nobel Prize of 2022 was awarded. And yeah, it's possible let me put it this way. It's absolutely certain there's something going on that we don't understand. Our concept of space and time does not provide an answer for why entanglement can exist. It's a property of the quantum world, and maybe in my grandchild's lifetime, this question will be resolved. And to close, let's take a look at this cartoon provided by my cousin. Whoops. Bear with me for 1 second. Let's go to this. And what is he? Oh, yes. He's saying Jumbo keeps turning upside down. And the master of ceremonies at the circus says, oh, drat, he's entangled with that elephant in Buenos Aires again. One is up, the other one's down. So with that, we're going to close out. I'll see you next week, and we'll have more quantum fun.